Right, this is our final lesson on two-dimensional trigonometry and associated topics. So we're going to be looking at section 2D of our textbook today, and this is the principal topic is the area of sectors. And we've already seen the arc length of sectors, so this isn't like a huge leap in a different direction. It's just a little bit further information to something you already have. Now, I just want to go back and review the arc length formula. So if you drew a sector, which is like, a conventional standard slice of pizza with a curved crust and two radii, projecting toward the center, we know that it is the angle, the subtended angle, the middle, draw that. So here they're using the symbol alpha. That one times there's a radius there. So the arc length is the circumference of a circle is 2 pi r, and we just want that portion that relates to this angle here. And the formula that you've seen before is theta over 360. It's just been simplified differently over here, times 2 pi r. Now that's somewhere where we've already been. But now what we're going to do is we're going to be taking a look at the area of a sector. I'm sorry, I've scribbled all over it. I'll fix that in a minute. And it's exactly the same thing, but it's relating to the area of a circle because a sector is a portion of the area of a circle. All right, I made a bit of a mess here. Let's take a look at this another way. Here's the two formulas. They're in the formula kit. So this is the one that we did a while ago, and this is our new one here. You can see there's very, very close similarities between them. The key difference is this. That's the circumference formula. This is the area of a circle formula, and it's the portion of which that we're going to take. The skill now is to develop how do we actually use these. Here's a circle I've drawn, and I'm going to look at two things. In orange, I'm encoding up the area, which is obviously the space inside the circle, and in purple, you can see the circumference of the circle. Now, here's where the similarities are. If I draw a sector whose subtended angle, that's just a fancy word for the angle at the center, or central angle, is theta, what I do is I realize that that is the portion of the circle related to theta out of 360, because of course a whole circle would be 360, and this blue portion is just the theta portion of it, and we'll fill in the number later on. And that's why it gets inserted as a scale factor right in front of either the area formula or the circumference formula, and that's basically where it comes from. And those are the formulas that you know from the formula kit. Of course, it's not a C here anymore. Now it's an L for arc length. All right, let's take a look at this question. Now, this question is going to start off with something that we've done before. This is dealing with arc length, but I'm going to amend it to embrace the new idea here. It says 2 points A and B lie on the circumference of a circle. The radius is r, not given. And we do know that the arc length is 10.9, that's given here, and it subtends an angle or a central angle of 52 degrees. Most of they use that word subtend as well. Find the value of r. Okay, I'm going to put everything I know, theta and arc length, into the appropriate formula here. Arc length is, and just do an NSOF, what's point, and then you end up with this value here of 12.01 approximately. And there it is. Now, notice, but be really careful when you're reading these questions that you don't miss out a small detail like this one. This is an unconventionally designed question in that they didn't want you just to stop with the radius. They wanted you to process that and say, hey, what's the perimeter? Well, perimeter, as we of course know, is when somebody does a little walk all the way around the object. And in this case, you'll have completed the radius 2 times and the arc length 1 time if you're going to get all the way around the object, and that's why the answer is 34.9. Now I'm going to add an extra piece, an extra little twist to this problem that the original authors didn't put. I want to work out the area of the sector overall. And again, the normal inputs for this are theta, the angle subtended at the center, and the radius. So that's really no different than the arc length formula. Same too. But in this case, you'll see that we already have r from the previous answer, right? That was the most recent answer as computed on our calculator. So I'm going to use that. So that will form the radius portion here. What's it doing that for? I don't like that. It's going to make the radius portion here, and then the 52 degrees is over there. What does that give me? It gives me 65.5 square centimeters. Let's move on here. Now, I'm just going to, this is classic IB. They're going to give you a shape like a sector. They're going to tell you bits about it that are conventional inputs, and they're going to take away conventional inputs. In this case, they take away the radius, and you have to work back to find it. I really strongly encourage people to make a little diagram. It's a safe place where we can store clues given to us and also store variables that we choose and see how they all relate to one another. And that frees us up to look for a formula that we think is appropriate and use it appropriately on a calculator without having to remember all this stuff simultaneously or go back to the question to try and hunt it down. So you see I got a sector there, I just drew it, and it says that the area is 24 square centimeters. Subtended angle at the center is 60 degrees. Find R. That's a classic end solve. Just put the area in, make your subtended angle 60 degrees, and now you can just solve for R, and you'll see it's 6.77. And there, you can unravel all this algebra if you want to. There's no reward for it, and so in my mind, there's no point in doing it at this point. You have technology that can do it for you. The last thing we need to talk about is something called a segment. A segment is an unusual shape here. It's what happens when a chord, a C-H-O-R-D chord, which is not the diameter. A diameter is a type of chord. It's a special one that happens to go through the center of a circle. But in this case, this chord doesn't. And so it chops off that little piece, and that's called a segment. That segment is related to the sector that would house it or hold on to it. I'm going to draw a couple of radii over here from the center going out. Notice that the segment is a part of that sector that I've just drawn there. And here's how we access it. So if you want to find the area of a segment, and that's where this is going, I want to find the area of that shape. It starts off with the sector because we know the sector completely includes the segment. Right? So, and if you were to take a new line, this chord here, and I'm going to put a couple of hack marks on it there. There they are. That chord right there is one that segregates the sector into two bits. The first bit being the segment that we're looking for, and the other bit being the triangle that we don't. So what does that mean? We know from recent previous work, that the area of any triangle is 1/2 times the square of the radius times the sine of the subtended angle. Now we remembered it as A times B, but that's just the two sides that contain the angle. And since they happen to be the same in the circle, both being radii, the formula makes a small transformation like that. Okay, so then we've also very recently, have the area of a sector formula. So if I bring all this together, you can see that the segment that we want is actually housed inside this sector, so long as we peel off this triangular part from it. And this piece over here is a match for this shaded piece here. So then we got to redefine this using algebra, using our formulas. And here's how we do that. We're going to say that the segment area, this gray shaded spot over here, is the sector that contains it and this triangular top, and then take away the triangular top. And so that difference. So there's not a direct formula for a segment. It's kind of a combination of two formulas, put together in a very precise and special way. Okay, so we have the sector area formula, which we've just seen recently, and this is a modification of the area of a triangle formula. It used to be A times B, as I've intimated before, but now they're both R because we're in a triangle that's nestled into a circle whose vertex is at the center. And now for this particular one, I can go ahead and put all that information in there. The subtended angle is 74 degrees. The radius shows up a number of times, and there's the subtended angle again. And finally, you can see all of this accurately put into our TI calculator. It gives us a straight answer. This is not an end solve because there's no variable in here that we're trying to solve for. We're just going to compute what all those numbers do. Now, when we get into the homework set, you will recall that we did in 1J, we were dealing with arc length. And there's a question down here, number 4, and I've been keeping my eye on it for a while. And it doesn't ask this, but I want to imagine there's a part C. I would like you to find the area of this overall shape, which is, this is not a semicircle here. I've seen students before, convince themselves that that's true. It's not true. It is a segment on top of a rectangle. Kind of looks like the Gmail symbol. Or you could look at it as a sector here on top of this unusually designed shape. But you work it out. I'll put up a model solution for it after you've had a chance to try. But principally, we're working from section 2D. Whoops, I went a little ahead of myself here. And we're working from section 2D here. And the questions are all variety of sectors and segments, and you're going to have to keep track of what's going on. And the other thing is, sometimes we're going to nestle certain or inscribe certain polygons inside circles and ask about, how much of the circular shape is taken up by the hexagon inside it. And you just got to work it out. It's a bit of a puzzle, but you can see that basically the principle or the notions of segments and sectors is all over the place here. So that's it. We're right here now, gang. We've completed the sine rule, the cosine rule, the areas of triangles, and now we've got the areas of sectors, and that will wrap up 2D trigonometry and associated geometry, and this is our last one. So please be working on that one problem from 1J, that one that I modified, and also can you be working on these questions here from 2D, and that's great. Okay, let's get working.